Science Friday. Science Friday. Oh, yes.
Hello everyone, welcome to Science Friday.
Here's some for E as well. The one on the top here is one of the ways that you can define E.
What makes a field more likely to have an unbalanced gender distribution?
So this can be like, in the case of this paper, gyrification or brain folds.
This goes back to balancing information retention.
Incredibly negative.
We have to do information privacy.
As I think many of you know, some of you may have taken my classes before. I used to teach at Nueva. Currently, I'm working as a machine learning engineer at Blue River Technology. And just a quick disclaimer, I'm not here on behalf of my company. I'm giving my own personal opinions. It's my own personal thing. It's not related directly to the work that I do. But yeah, I'll be talking a bit about detecting bias in machine learning models. So roadmap for today. We're going to get a quick understanding of some of the difficulties of teaching computers. So for those of you who have not worked with machine learning before, don't worry, I'm going to talk through enough to understand what the issues are that this paper was trying to look at. Give you a couple examples of things that have gone wrong, and then we'll talk about the paper, the tool that they've proposed for trying to mitigate some of these issues, and talk about what we do and don't like about their method. So the main thing that you need to understand in order to understand what they're trying to do is that machine learning is about finding patterns in data, usually lots and lots and lots of data. Because the idea is that we're going to give enough examples that it can start to put together answers from even complicated things, like, for instance, natural language text, like the text that you and I might use to communicate. So an example is the fancy name is sentiment analysis model, which is basically just trying to say, what emotion was the person writing this feeling at the time? So a really simple model like this might say, is this a positive thing or a negative thing? So maybe you're talking about like movie reviews or product reviews or something like that. So if you can imagine, there might be some that are really simple, at least for humans. Say, this was great. Okay, that's a positive review. This was not great. Okay, as soon as you put that not in there, it's a negative, right? And similarly, you could have this was terrible, this was not terrible, obviously negative, positive. But then as you start getting longer reviews, it becomes a little bit more complicated. So there's a not and a great in there, but the not's not with the great, so it doesn't change, it stays positive, right? And in addition to that, the model is going to have to learn a whole bunch of slang, right? Because good and bad is one of the things that we find tons of words to cover. And so the model is going to have to learn all of these tend to mean, either good or bad, or sometimes they tend to mean both, right? Back in the 80s, we used to say things were bad, meaning they were good. I don't know, it was a weird time. So in order to be able to figure out really complex relationships like this, you have huge data sets that we're using. Now, the paper talks specifically about finding issues in images. So the rest of the examples I'm going to give are about images, but I just want to make sure everybody understands machine learning can happen on all kinds of data: text, images, videos, music, numerical analysis, anything that can be translated into digital representations. You can run machine learning on it, with more or less success, depending on how good your data are. The other thing I would say, I'm going to give a few examples. If you have seen these examples before, please do not blurt out the answer. Let other people get a chance to try to think through. So here's one example of a program that was trying to be able to tell different species of animals from one another. And it was amazingly good. It could tell even things that humans might sometimes have trouble with, such as telling a Siberian husky from a wolf, right? Especially in some images, it might be a little bit tricky. So I want you to turn to the people around you and discuss, thinking about a computer getting a bunch of images like these, what differences do you think it might be noticing in order to be able to tell the difference between a husky and a wolf? I'll give you just a few seconds to talk. Okay, and just a note that with the virtual thing, you guys are muted, so I really can't tell how much you're talking or not. So my apologies if I'm totally interrupting conversations going. So what are some things that people came up with? What are some of the differences you notice?
Like raise hand. Yeah, Micah.
We talked about fur patterns.
Great. Yep. What else?
Let's go. Aura and then Akshar.
Maybe if you have pictures of like more of the animal, you can tell by the size.
Great. Yep. Yep. It's, scale can be very hard to tell in photos, but if they're all in a similar scale, absolutely size. And if they have anything there for reference, then size could be part of it. Yeah.
Akshar.
There's also like fur texture.
Yep.
Caroline, you're gonna have to speak loud.
If there's like a collar or leash.
Yeah, Caroline said if there's like a collar or a leash.
Yes, great. So the huskies are much more likely to have something like that, something human made, for sure. Anything else? Okay, so these are all really great things to notice, and we notice these because we're humans. We understand the question that we're trying to ask and how all of those things are relevant. The problem is that computers cannot necessarily tell what's relevant. And what the computer noticed is that wolves are usually photographed in snow, and huskies are usually photographed in other backgrounds. So it was very, very good at being able to tell snow from other backgrounds. However, it was not actually at all good at telling huskies from wolves. So definitely an issue with the data set where they were not careful to make sure that there was a variety of different backgrounds for the animals. So here is another example, and this one I'm going to start with the problem. A researcher was looking at another model, and again, we would call all of these classifier models, meaning that they are attempting to look at something and say, what type is it? And so when they were putting in pictures such as this, grassy meadows, the computer would respond sheep. So again, take about 30 seconds, turn to the people next to you. Why do you think a computer might look at something like this? Like, what do you think it might have seen as its training examples to say, oh, yeah, this is sheep?
But then also cows.
Uh-oh.
All right, if we can all come back together. And so if some people want to share some of the ideas that you came up with.
Yes. Yeah, Charlotte.
The picture has a group of white fluffy gloves and
Sorry, I couldn't quite hear that.
She was talking about how the picture has a bunch of white fluffy blobs. And what was the other thing?
there's also
Yeah, so one possibility might be that a bunch of the pictures of sheep were like really out of focus, or like almost all of them were, enough so that the computer learned that anything that has kind of a white fluffy mass could be sheep. Yeah, that's a possibility. Other things that people thought of?
Yeah.
if you look at pictures of sheep, many of them are kind of photographed in this sort of stereotypical field with a fence and maybe some, stuff in the background. But honestly, I could imagine somebody just photoshopping sheep into this picture and it will look normal.
Right. So yeah, this would be a very common place where you might find sheep. Exactly. So it could be that a lot of the examples that the computer saw were, fields of sheep, and it just learned that the entire thing, that's what it means to be a sheep. Any other thoughts that people have? Yeah, and so in this case, the person looking into it wasn't in control of the model, so they couldn't tell for sure, but that was their best guess, is that all of the images were of sheep had a meadow, or conversely, all of the pictures of a so like maybe the sheep had a variety of different backgrounds, but the only time an image like this, like a big grassy image, showed up was when there were sheep in it. And the other thing to keep in mind too is when you have a classifier model, it has a limited amount, a set of answers it can give, right? You've told it these are all of the possible things, right? So if there was no option for grassy meadow, then it would just have to learn something that was the closest it could get. And again, that might be sheep if that's when it generally saw images like this. But again, this comes from the computer. We think we're telling it what question we want, of like, tell us like the main part of the scene. But all it knows is the data that it's given, right? And so it doesn't have any kind of contextual information. We just haven't figured out how to make computers do that yet. So that it would be able to understand that, maybe the fence would be the most relevant part, or the overall scene. But when you see the sheep, then we say, oh, there's sheep there, because as humans, we go straight to the animals if we're looking at a photo. All right, so those two, wildlife images, maybe not the most crucial for the system to getting right, depending, I guess, on what you're trying to do with it. But this next one, my last example, starts to get into where you see a little bit more consequences from getting it wrong. So again, I'm going to give you 30 seconds, and again, do your best to think like a computer. Tell me all of the differences that a computer might notice between these two X-ray images. So talk to people around you again. And if you can wind up your conversation. Thank you. Cool. What things did you notice that were different between the images?
Juliet. So Juliet said one of them is a lot sharper and brighter.
Right. Yeah. So one of them is definitely quite a bit sharper. Yep. What else do you notice?
Yeah, Micah.
There is a less dense spot on the our lower right side of the left image.
There's a what spot, did you say?
A less dense, a blacker spot on the lower right side from our perspective of the left image.
Yeah. All right. What else do people notice?
Shara and then Laura.
The image on the left is smaller than the one on the right.
Yeah, so Shara said the image on the left is smaller than the one on the right.
Right. So and that might be a question. Is this a smaller person, or at that facility, do they take the X-rays from slightly further away? But either way, something the computer might notice for sure. Anything else?
Laura?
On the right, the shape of the lungs is just a little bit different. It's like more diagonal versus the one on the left is more like kind of straight.
Oh, the ribs?
Yeah.
Right. Anything else?
Yeah, sure.
I mean, if those text annotations on the top right and left are, part of the image, then there might be a correlation between what those are and some sort of facet of the X-ray, and that might be helping misinterpret them.
Yes, in fact, the text on the X-ray is going to vary by hospital. So all of these are great things, and some of them we would want the computer to notice, right? They're things that actually have to do with, is this person suffering from some kind of issue that can be picked up on the X-ray? But other of them, totally irrelevant. How sharp the image is, what kind of text there is, and that is not just random, it's actually going to give you information about where the picture was taken, or at least that, all of these images were taken at the same place, all of these were taken at a different place. And so there was actually a very specific example of this. So in mid 2020, there were a lot of data sets coming out from the pandemic of patients who had COVID-19 and who didn't. And the big thing was like, oh, would machine learning be able to tell, to diagnose it essentially just by looking at the lung x-rays? And some papers seem to say, yes, absolutely, they could. And in one of those cases, it was particularly egregious. All of their COVID positive patients came from one hospital and all of their negative came from a different hospital. So all it had to do was notice some, difference in the font or the annotation or the sharpness or something like that, to be able to get a perfect score. In other cases, it's a little bit better, but still what they found in some of the cases was that the machine learning algorithm essentially learned that about 70% of cases in this area were positive, about 20% over here. So if I just go based on area, I'll get it reasonably correct, right? So, fortunately, none of this was being used in clinical settings. It was all just testing out these ideas. But you do have to be very, very careful about making sure that you were using the information you wanted, things that people were pointing out about, maybe the shape of the ribs or the shape of the heart, things like that, and not the information that we know to be irrelevant, but the computer can't tell it. As the person with the text, it's just part of the image. It doesn't know any better. So in these paper that I'm talking about today, they had a few specific examples that were top of their mind, either in some cases because they had worked on projects like these or worked on finding bias in projects like these, or because they had personal experience with machine learning not working for them. One of the researchers had facial recognition systems not work for her, right? So all of these are examples of things where the machine is picking up on information that we would like to be irrelevant for the question we're trying to ask, but it's learning some of the biases that we have in our society, or it's just picking up on the biases in the data set, right? So if you don't have very many examples of people who have darker skin, then your model is not going to work very well in darker skin. If you don't have many examples of various different genders, then you're not going to work well on those, right? Because the computer only learns from the examples it's seen, right? And this could potentially have huge consequences in pedestrian detection. If you're talking about a self-driving car, that's talking about somebody's life, right? So we cannot afford to be getting things wrong like this. And just to add a couple other examples that weren't in the paper, things like who gets a loan, how long your jail sentence is, whether or not you get into a certain college, what financial aid you get. All of these are sometimes at least decided by machine learning models today, right? And we really need to be looking into whether or not it's operating on the information that we want it to, as opposed to the information that we gave it because we weren't thinking hard enough about it. So the point of this paper is to figure out what's one tool at least that we could use to try to test if our model is answering the question that we actually wanted it to ask. So their particular solution involves more machine learning. So what they wanted to do is be able to have a data set that they could control easily so that they would be able to test out a classifier and see, if as I adjust certain things, does it react in the way I would expect it to? So they use what's called a generator model. So far we've been talking about classification models, and classification models are trying to, like I said, label something, decide what something is. A generator model is trying to take a bunch of examples and say, here's something that's sort of like that, right? So many of you have probably seen things like deep fakes. Those would all be generator models, right? We're trying to take a bunch of examples and create something that looks like them, but is novel. So in this paper, their proof of concept, specifically, they took a data set of celebrities that had been annotated previously with things like, what color is the hair? What color are the eyes? Are they wearing a hat or not? Are they wearing makeup? And also, interesting enough, are they young, as a yes or no question, which seems a little fraught, but that's what the data set was. And so they decided to take this and create a generator and use that generator to test a classifier model that would try to detect if somebody was smiling or not in a photo. So they did take some steps to try to balance the data a little bit to make sure that the smiling versus not would be reasonably balanced across the various different characteristics, especially since some of them are fairly well correlated. So just trying to tease some of that out and reduce some of the bias that was in the data set that they could see already. So here's just an example of something that their generator did. They asked their model, create two faces with all of the same characteristics, but one has facial hair and one doesn't. So you see, I think, at least for this example, it did pretty well. I would probably guess that these two people were related. And so, you know, what this shows is that you have something where you can start to manipulate individual characteristics and then see, does changing just that characteristic change the answer when it shouldn't. So here's another example of things their generator produced. And what they found was, because of the way they had implemented it, they could actually do a continuous or semi-continuous movement of these characteristics. So even though their original data was just yes or no, or like, you know, a simple like what color is this, they could actually move along a gradient. So as the generator learned a little bit more about, you know, what it means to have facial hair or look young, or have, you know, different color hair, or different length, it could actually say, you know, not just 1 or 0, but across the gradient. So as these images go down, the idea for the generator is that they should look younger, which again, I think did a reasonable job. The people look younger to me. And so now that they have all of these different images, they can start putting them into this smiling classifier and say, okay, does it change whether or not it thinks it's smiling? Because, you know, as humans, we think being young should not affect whether, you know, if a person who has the same mouth position, it should not matter if they're young or old. You should still probably have the same probability of thinking that they're smiling. And in fact, their classifier did have little change as you move the amount of youngness for the photo. But they did find some examples where that was not true. So for the lipstick parameter that the generator could do, it did actually have a big effect on guessing whether or not they were smiling. And again, you can look at these photos. The mouth position doesn't really change. I mean, to be quite honest, I look at it and say, well, I don't even know that the lipstick changes all that much. Like that's a really subtle change there. And yet it had a big effect in the classifier. So the overall accuracy was about the same for somebody that was wearing, you know, 0 lipstick according to generator, or 1 amount, like the full amount of lipstick. But it totally changed the ratio between false positives and false negatives. So if the face had lipstick, it was much more likely to incorrectly predict that they were smiling when they weren't than to incorrectly predict that they weren't smiling when they were. Right? Whereas with the faces without lipstick, it was about an even split. Right? So here was an example of where their tool was able to find something that clearly there's something going on here where the model is learning something that we didn't want it to, right? There's no change in the facial expression of these images, so there shouldn't be a change in the prediction. So again, so this is their proof of concept, and the idea would be you could apply this to a lot of different models where you can think through, okay, what are the potential characteristics that I'm concerned about my model using that it shouldn't be to answer these questions, and then create a data set that would allow you to test that hypothesis. So I know we're getting close to time here, so I want to jump to talk amongst yourselves just for a brief bit. What do you think is a good idea about this tool? And then do you have any concerns?
Jack, only have a question. I can take
Okay, and if you can wrap up. I do want to leave a little bit of time for questions. So rather than hearing what people said, I can, if you want to comment at the end, I'll let you do that. But I just really quick wanted to share a couple things that concern me, and then I'll answer any questions you have. But yeah, I think it could, as part of a set of things you were doing, absolutely, it could help. I think it would, if you did this technique, would absolutely push you to really understand your data set better, and to notice issues that you might have missed. The kind of downsides here are, it does require you to actually think specifically about what things that you want to test. And so there may be some that are obvious, but not others. And given that one of the big issues within the machine learning field is the lack of diversity of different perspectives, I would worry about there not being somebody who would notice some of the things that you ought to be testing for any particular problem. I'd also worry that many of the biases you might be testing for could also be in the generator itself, and it would cause you to miss it, right? So if you don't have examples in any of the data you're using of some of the issues, the generator is not going to really produce good examples of those. And so your model might not respond to it, but it's not because it doesn't have that bias, it's because the things the generator producing don't have it either, right? So, the generator could be very off on what you're actually trying to produce. And also just the large effort, I would worry about that, meaning people go, oh, that's too much. I'm not gonna do that. But although again, the flip side is if they do it, it really does help them understand the data set. So that's good. And then just the last thing of you might wonder, why is this important to me? So I've actually worked on and off in machine learning since 2004. Back then we didn't even call it machine learning. My company, we called it statistical modeling. And as more and more things have come out, there have been different things where I've realized, oh, I wouldn't even thought to have worked on that. And mostly I've been lucky that the things I was working on just happened to avoid some of the different controversial issues that have been pointed out lately. But definitely, as I was doing my job search last year, that was a big issue of wanting to make sure I wouldn't look back on what I was doing 5-10 years from now and go, oh no, I totally missed this this thing that I really should have seen, and that would have changed how I would do my work. So many of you may be in that position someday of deciding what you want to work on. Maybe you're already in some position and there's the opportunity to use machine learning. And I just want to make sure that you understand some of the issues that could arise, and make sure that you go through that process of thinking about the potential pitfalls and whether or not you should even pursue the project given the technology that we have. So I think I have 2 minutes left if anybody has questions.
No, it's all good.
Okay. Okay, everybody, thank you so much for coming. This was Jen Selby. Why don't we give her a hand? Next week, we have Jack presenting on language modeling and